Hey guys, and welcome back. Today we're going to be finishing up volume of a sphere. We're looking at activity 36-2, page 531. It's kind of a good reference page. So what I want to do is run through questions 11 through 18. We're going to kind of go through the answers there, make sure your work is good, and make sure you didn't have any questions there, okay? So we're going to start with number 11. Number 11 deals with the idea of what would the volume be for 1/4 of a sphere. And so we simply take the formula for the volume of a sphere and you divide by 4. If the original formula was 4/3 pi r cubed, the final answer now is going to be 1/3 pi r cubed, or pi r cubed over 3. All right. Number 12 talks about why is it that the surface area is in units squared, whereas the volume is in units cubed. And just remember, the surface area is like the amount of paper it takes to cover the globe, versus the volume is how much stuff's on the inside. Okay, it's 2-dimensional versus 3-dimensional, and that's why. 13 talks about finding the volume given the diameter is 8, which means the radius is 4. So that would be 256 pi over 3 once you plug that in. For all of mine, I'm going to give you kind of the fractional answer, and you're welcome to plug that into a calculator to verify your decimals, okay? So that would, number 13 would be 256 pi over 3. Number 14, they tell us that the surface area is approximately 314, which tells us that our radius is 5 when we solve that, okay? 314 is about 100 times pi, and 100 pi divided by 4 would be 25, meaning that radius squared would be 25, so the radius is 5. And then we plug that in to get our volume, and we end up with 500 pi over 3, okay? And again, you can put that in a calculator to get your decimal answer. Number 15, we have a hemisphere. Remember, the formula for a hemisphere is we just cut the volume in half. So instead of 4/3, we're talking 2/3. So 2/3 pi times 4.5 cubed is 4.5 because the diameter is 9. So don't forget to cut the diameter in half. And then when you plug that in, you should get 182.25 pi divided by 3. All right. Number 16, we have a radius of 7 because the diameter is 14. And we know that based on the information they give us. And so, oh, bad teacher, I just wanted to look to make sure I was on the right track, and I'm not. So we're going to fix 16, and this happens, right? As you're going through problems, something goes wrong, so we're going to rewrite this. Notice that it's not the diameter that's 14, it is actually the radius. So I'm going to put in the radius here, which is 14 to the third, okay? And so you're going to have 4/3 pi times 14 to the third, and that's going to give you your answer. Going to be a nice huge number. 14 squared, 196, and then 14 times that is going to be 200 or 2,700 and something. Times 4, you're looking at like 10 grand divided by 3. So you're going to get a huge number here. Your answer is going to be 10, 11,000, something like that. It's going to be a nice huge number. And it should, right? Because we're using a radius of 14, whereas we have been using very little radiuses, okay? And I'll let you plug that one into the calculator. I don't think there's a lot of stress there. Number 17 and 18 I like. They are both applied-ish problems. Number 17 is some golf balls that are stuffed inside of a box. In fact, there's 4 golf balls stuffed inside of a box. The box is 2 by 2 by 8, giving the box a volume of 32. Remember, volume for a box would be length times width times height, or base times height, capital B. And so we get 32 inches cubed, whereas the golf ball themselves, there are 4 of them, and it's 4/3 pi r to the third, but in this case r is 1, and 1 to the third is still just 1, so it's really 4 times 4 pi over 3, which becomes 16 pi over 3. And so if we want to find out how much space is left over, how much volume is left over, we're going to do the volume of the box minus the volume of all 4 golf balls together, and that gives us 15.2, which is way more than a fifth golf ball. It turns out that a sphere inside of a box really only takes up just over half of the volume of that box. So there's a lot of extra air, a lot of extra space. All right. Number 18 is interesting. You have an ice cream cone, and they want to know if the ice cream melts, will it overfill the cone? Okay. And so we have to remember the cone volume is 1/3 base times height, or you might see it written as pi r squared h over 3, or 1/3 out front. Pi r squared is the shape of the base, okay? And so we kind of plug that in. They give us our radius is 2, so we get 1/3 pi times, this is pi 2 squared, which is 4 times 4, so we get 16 pi over 3. And I left it in terms of pi. You can get a decimal, that's fine. But when you work the sphere, you get 4/3 pi 3 cubed, and you get 102 pi over 3. Obviously, this number is far greater than this number. That tells me there's going to be a lot of ice cream left over, okay? That's why when you're eating your ice cream, you still struggle with the idea of it actually running down your hand, because the volume of the sphere far exceeds that of the cone, all right? So that's 11 through 18. Hopefully that made sense. Now we're going to kind of go a little different way. I'm going to give you the assignment for the end of this section. I know there's one more section left, but we're going to talk about that. It is, shall we say, kind of an extra. It's a little more necessarily than what we normally cover in geometry, but I do want to talk about it with you for a second. But let me give you first, the assignment is going to be on page 537 through 538. You're going to do questions 1 through 11. Skip 12 and 13 because they're going to be about spherical geometry, which we're about to talk about. And then do number 14, okay? So spherical geometry, everything that we've done so far is called Euclidean geometry, and it's dealing with what happens on a plane, what happens on a flat surface. Spherical geometry is talking about the idea of things that happen on a sphere, right? So let's say we have a sphere. And so I'm gonna go over one idea, kind of probably one of the biggest ideas that the only thing we really ever test on spherical geometry is if I were to take that sphere, right? And everybody can kind of picture that as a sphere, hopefully. And what I want you to imagine is that I'm going to draw a line. Think of like the equator going around the globe, right? So here's my equator. And then I'm going to draw a longitudinal line straight down through the middle, okay? On the outside of the globe, but still straight down through the middle, right? And most people are okay that this is a 90-degree angle. Can we all see that? Can we all agree with that? Okay? Now, if I were to rotate that globe 90 degrees, and so I'm going to be over here, and I draw another line right here, okay? So I have another line right there. This angle is also going to be 90. And this angle up here, if I do it at a full 1/4 of the way around, it's going to be another 90. But let's say it's not. Let's say it's not, doesn't matter, 80, 70, 100, whatever. Notice I have 90, 90. What I've created here on the surface of that ball is a triangle, but what does not hold is triangle sum theorem. Triangle sum theorem was the idea that in a triangle, the total number of degrees are 180 degrees, okay? Basically, if you were to imagine cutting a line down this way, cutting a line across the ball, and then cutting a line here, you could have 3 90-degree angles. There would be 270 degrees inside one sphere, or inside one triangle, so the triangle sum does not hold. So really with spherical geometry, that's the one thing that I just wanted to make sure you're good with. Also, the idea of great circles. Great circle is going to be any circle that would cut the sphere into 2 hemispheres, okay? So any circle whose center would be the center of the sphere, that's going to be called a great circle, and it's going to go all the way around. And I know we're used to, on globes, we have latitude and longitude, but technically great circles can go any direction. They do not have to go straight up and down or straight left and right. They can go diagonal, they can go any direction, but they go completely around the shape, okay? And those are called great circles. If you'd like to know more about spherical geometry, there is this section, pages 532 through 536, going over spherical geometry. You're welcome to read through that. You're also welcome to do research on your own. However, for this course, for H-squared-I, we do not require it, okay? I hope that makes sense. Reminder, your assignment, page 537 through 538, we're going to be 1 through 11, skip 12 and 13, and then do number 14. All right, good luck, guys.